Hello, my dear students. Welcome to online classes on design of mission elements. I am Dr. Bharat Vinjamuri from Global Academy of Technology. In today's session, we'll be discussing how to solve numericals in this subject. We'll be mainly focusing on numericals on axial, shear as well as bending loads. Before starting the numericals, let us revise the basic formulae in solving these numericals. These are the textbooks which I'll be using throughout this course. Shigless Mechanical Engineering Design by McGraw-Hill Publishers. Design of Mission Elements by V.B. Bhandari from McGraw-Hill Publishers, as well as we'll be exclusively using a Mission Design Data Handbook by Lingaya from Summa Publishers. So the data on the formulas are taken from this Mission Data Handbook. This is the table which we'll be making use of while taking the shear, moment and deflection formulas in case of beams. Especially the third column as well as fourth column will be considered while solving the numericals. In the third column, we'll be taking the maximum bending moment, and in the fourth column, we'll be considering the maximum deflection. So this table gives the values for beams subjected to different types of loading and end conditions. Now this table number 2.8 is continued for next 3 pages. You can see here a simply supported beam with uniformly distributed load has also got a maximum bending moment and maximum deflection. These are the formulas which will be making it used in the numericals. Now this table which you see on the screen will be making use of this table to determine the properties of cross sections during bending. Now this table gives the values of section modulus for different cross sections. Also we can see the values of moment of inertia using this table. Note that in this table, for especially in case of rectangular section, cross section, the parameter B or the dimension B is exactly parallel to the axis and the dimension H is perpendicular to the axis. The same notations will be using it while solving the numerical. We will consider B, a dimension B, always parallel to the axis, and the height H or the depth H always perpendicular to the axis. So in this formula, BH square by 6, it is clearly said that the parallel dimension multiplied by perpendicular dimension square by 6. Similarly, the similar terms will be used while calculating moment of inertia. So even though if the cross section has changed, now as in this case, since the dimension B is parallel in this case, as well as the H, the perpendicular dimension is always considered as H, the parallel dimension is always considered as B. In the previous video session, we have learnt how to determine axial tensile stress as well as axial compressive stress. In today's video session, we will try to find bending stress in the components subjected to transverse loading. Let us start the numericals. A beam of uniform rectangular cross section is fixed at one end and carries a load of 1000 newtons at a distance of 300 mm from the fixed end. The maximum bending stress in the beam is 80 Newton per mm square. We need to find the width and depth of the beam if the depth is twice that of the width. In this numerical, he has clearly informed us that there is a beam which is fixed at one end, which means that he is talking about cantilever beam, and the load of 1000 newtons is applied at a distance of 300 mm from the fixed end. It means the total length of the beam is 300 mm, and at the free end there is a load of 1000 newtons which is applied. Also, the beam has a rectangular cross section having a certain width as well as depth. Also, in this numerical, he has given the relation between the depth and width. He has clearly mentioned that the depth is twice that of the width. At the same time, he has given the bending stress of the beam as 80 Newton per mm square. Let us solve the numerical by writing down the given data. This is the pictorial representation . So substituting these values in this equation, sigma b is equal to mb by z. Let us first calculate the bending moment. Mb is equal to F into L. F is 1000 and L is 300 mm. We'll be getting the bending moment as 3 into 10 power 5 Newton mm. After finding the bending moment, we'll substitute these values into this equation. Now, since in the numerical he has given depth of the beam is twice that of the width, now we can substitute this value in section modulus equation obtained from table 2.7 from design data handbook. Instead of h, we'll be having the equation of h is equal to 2b. So by substituting h as 2b in the equation of section modulus, we'll be getting the section modulus z as 2b cubed by 3. Once we get the value of z as well as mb, we'll be substituting the values of mb and z in the equation sigma b is equal to mb by z. So substituting these equations, sigma b is equal to mb by z. Sigma b is 80 Newton per mm square and mb is 3 into 10 power 5 Newton mm and z is 2b cubed by 3. We'll be getting the value of sigma b as 17.78 mm. Since we know that h is equal to twice the width, we'll be also finding the value of h as 2 into b. So 2 into 17.78 mm, 35.56 mm is the answer for h. Thus, we will be able to find the value of width and height of the cross section of this cantilever beam. Let us solve one more numerical on transverse loading. This time, the numerical is based on a circular cross section. The previous numerical was on circular rectangular cross section. This time we'll be solving this numerical based on circular cross section. A circular rod made of C40 steel is simply supported between the bearings. So it is understood that the type of beam which we are going to deal is simply supported beam of 1.8 meters apart, means the total length of the beam is 1800 meters, mm. It carries a central load, so the load is at the center of the simply supported beam of 6 kilonewtons or 6000 newtons. We need to find the suitable diameter of the rod. Also, he has given us factor of safety 2.5 he has given based on the yield stress of 328.6 megapascals. So for C40 steel, the yield stress is given as 328.6 megapascals, and also he has given a factor of safety of 2.5. So it is evident that by using these two values we can determine the allowable stress. Allowable stress can be obtained by dividing the yield stress with factor of safety. Also, he has given one more condition, that the deflection in this beam should not exceed 3 mm at the middle. So this problem we need to deal twice. One, we need to find the diameter based on the bending stress equation sigma b is equal to mb by z, and also we'll be trying to find the deflection diameter based on the deflection equation y maximum. Let us solve this problem by writing the given data. So we can see a pictorial view where we have a shaft rotated or placed between two bearings. But by considering these two bearings as support and the load acting at the center, the pictorial view of this diagram can be seen on the figure. Can be seen in this figure. So there is a simply supported beam of length 1.8 meters or 1800 mm. There is a load acting at the center of the beam of 6 kilonewtons. The beam is having a cross-section area of circular cross-section having a diameter d. We need to find this diameter d. The material of the beam is given as C40 steel. The length is given as 1800 mm. The load is 6 kilonewtons, which amounts to 6000 newtons. The factor of safety is 2.5. The yield stress is 328.6 megapascals, and the maximum deflection it can withstand is 3 mm. We need to find the diameter of the rod. Since he has given factor of safety as well as yield stress, we need to determine the allowable stress for this material. The allowable stress can be determined by dividing yield stress with factor of safety. Therefore, the allowable stress is equal to sigma y by fys. So in some books, the allowable stress is also called as maximum stress or maximum bending stress or working stress or design stress. By substituting the value of sigma y and fys, we'll be getting the allowable stress as 131.44 megapascals. So in this entire numerical, we'll be using allowable stress value 131.44 megapascals instead of sigma y. So what is the basic idea? How exactly will we dealing this numerical? During this numerical, we'll be determining the diameter of the rod by using bending stress equation sigma b is equal to mb by z. Also, we'll be determining this equation by using y maximum formula or maximum deflection formula, which is available in the table number 2.8. This equation is available in table number 2.8. By finding both the diameters, we'll be selecting the maximum diameter out of the available two diameters which were obtained by using bending stress equation as well as maximum deflection equation. Let us start finding the diameter by using the first case, that is by using the bending stress equation sigma b is equal to mb by z. Case 1, the diameter of the rod is d, which we'll be trying to find by using the equation sigma b is equal to mb by z. In this formula, the bending moment mb is fl by 4. This equation is obtained from data handbook table number 2.8 for simply supported beam. The value of F is 6000 newtons and L is 1800 mm divided by 4. So we'll be getting the value of bending moment as 2.6 into 10 power of 6 Newton mm. We can also determine the value of Z provided. So the diameter is given, but in this numerical the diameter is not given. So we'll be finding the diameter by using the equation Z, the value where the Z is the section modulus of the cross section. For surplus section from table number 2.7 in design data handbook, the equation for section modulus is Z is equal to pi dq by 32. So this is the equation which we'll be using it for circular section. The section modulus from table number 2.7 will be taking the equation as pi dq by 32. So the equation, once again the table has been shown in the larger view. So for this table, for circular section, we'll be making use of the section modulus equation. Okay, this is the equation which we'll be making use of it. So in this case, this is the equation which we are going to use for this numerical. So we'll start calculating the values. The sigma b value is 131.44 Newton per mm square, and also we have already calculated the bending moment as 2.7 into 10 power of 6 Newton mm, and we'll be finding the value of Z. By using the equation Z is equal to pi dq by 32, we'll also determine the value of diameter. So this diameter is obtained by considering bending stress formula. Now we'll also determine the diameter of the rod by using the deflection equation Y maximum. From table number 2.8 in design data handbook, the deflection equation for simply supported beam is given by FLQ by 48 EI, where in this case E is the Young's modulus and I is the moment of inertia. I'm referring to this equation which is obtained or which is available in design data handbook from table number 2.8, where Y maximum is equal to 1 by 48 FLQ by 3 FLQ by EI. Now in this case, the negative sign in this equation clearly explains that the beam is bending towards downward direction. So this is the equation which we are going to use. So by substituting all these values, value of Y maximum has been already given as 3 mm. Okay, Young's modulus is not given in the numerical. Young's modulus for steel can be assumed as 206.8 gigapascals or 206.8 into 10 power of 3 megapascals. The moment of inertia I can be also obtained from table number 2.7, whose value is pi d power 4 by 64. Now we'll be substituting all these values in this equation so that we'll be able to determine the value of moment of inertia. Now after finding the value of moment of inertia, we'll be able to determine the diameter d. So by substituting all the values of Y maximum, F, L cube, E as well as I or E, will be able to determine the value of I. In this case, the value of I is obtained as seen in the figure. After getting this value of I, we'll use the equation I is equal to pi d power 4 by 64. From this equation, we'll be able to determine the diameter d. Note that the diameter d in the case 2 is very much high compared to the diameter obtained in case 1. Therefore, selecting the maximum diameter for this numerical will be considering 69.94 as a maximum diameter for this circular rod. Let us solve one more last numerical in case of transverse loading. A 1 mm thick hacksaw blade is bent into a circular arc of radius 500 mm. So he clearly says that there is a hacksaw blade. The thickness of the hacksaw blade is 1 mm. It is bent in the form of a circular rod and the radius of bending is 500 mm. We need to determine the bending moment applied and also the stress induced in this hacksaw blade. Also, he has given the width of the blade as 15 mm and the modulus of elasticity as 200 gigapascals. Let us start working on this numerical. So there is a hacksaw blade which is bent as shown in the figure. The radius r has been given as 500 mm and the width, the thickness, this is the thickness. You can see the thickness as 1 mm. He has given this thickness as 1 mm and also the width. Okay, and now here the width of the blade is 15 mm. I'm talking about this width, where this width is 15 mm. We usually call this width as B. So there is a width as also known, and thickness is also known in this case. Okay, we need to determine the bending moment. So similarly, you can see such a case where the hacksaw blade is bent with a certain radius. So the given data, thickness as 1 mm, the width B is 15 mm and the radius of bending is 500 mm. Also, he has given the Young's modulus as 200 gigapascals. We need to find the bending moment as well as the bending stress sigma B. We'll be making use of table number 2.7 for a rectangular cross section H. Now instead of the equation BH square by 6 for section modulus or BH cube by 12, we'll be using BT cube by 12. We'll be using BT cube by 12 since we have used as T as the depth instead of H. T as the depth. So the bending, will be making use of this bending equation mb by I is equal to sigma by y is equal to a by r. In this case, to find the bending moment, okay, we'll be making use of these two equations. mb by I is equal to a by r. Okay, where mb is the bending moment, I is the moment of inertia, e is the Young's modulus, and r is the bending radius. So in this case, I is equal to bt cube by 12. We have obtained this equation from table number 2.7 design data handbook. So by substituting the value of B and thickness as 15 and 1, we'll be getting the value of I, moment of inertia. So substituting this value of I in this equation, we'll be able to get the value of bending moment mb divided by I as 1.25, and the value of E is already given in the numerical as 200 into 10 power of 3, as well as the radius of bending is 500. By substituting all these values, we'll be able to determine the bending moment as 500 Newton mm. Also, to find this bending stress, we'll be making use of this formula sigma b is equal to mb by z. mb we have already determined as 500 Newton mm. Now we'll be finding the equation for z. The equation for z also can be obtained from design data handbook. Z is equal to bt square by 6. This is also obtained for rectangular cross section from table number 2.7 design data handbook. Substituting the values of b and t in this case, b as 15 and t as 1 square, 1 into, so 1 square divided by 6, we'll be able to determine the value of Z as 2.5 mm. Since we got the value of Z as 2.5 mm and also we have determined the bending moment, we'll be able to determine sigma B is equal to 500 by 2.5, which amounts to 200 megapascals. Thank you for watching this video. In the next session, we'll be discussing on determining the torsional stress. Thank you. Have a nice day.